we have this production process. And I know this isn't what everybody's process will be. This is sort of, the fab, sort, assembly, test, pack are just designed to be steps that you might recognize in terms of that. But we have this production flow that goes along up top there. We have a order from the supplier and a receipt if it's done in an outside process. If it's an inside process, we have a production order and a production out. And really this movement of the process, along these things. And we want this to generate, this one process to generate all the information we need, WIP, inventory, yield, cycle time. This process is bigger than costing. This process is production control for production execution. This process is really lot genealogy, lot traceability, lot management. And so it really has that level of detail. But it's also how we cost things and how the semiconductor industry works and thinks about production cost. And so what we really have is this process of process manufacturing, and it is a process. It has fixed outcomes, so it's really not like food processing or oil and gas or paint manufacture. It's not a continuous flow process. It is a process, though, and it has these defined stages of production. Everyone on this call, when you were going through the implementation part of the process, came up with major and subcategories of steps of production, and they might be defined by when inventory value changes or by when you have costing or payment steps with your vendors or some sort of a hold point. Really, these are repeatable steps, and this is the 1, 2, 3 kick of FSM, where we have a order, receive, we consign inventory to the next step of the process, and so then this order here is adding value to the consigned inventory from the preceding step. And so we consign, we order to add value, we receive that, we have new material, we consign that to the next step, we order, we add value, we have new output, we consign that material to the next step. And it really is this order, receive, consign, with each time we do a receipt for a major production step or a minor one, we have a inventory value change that occurs. And really those become the points in standard cost where we say this is where we need a plan. We need a plan for what cost is going to be at each one of these stages. And we need to consider how we're going to value this inventory or this lot in process that we're going to consign to the next step. And so we sort of, if you think about it from a financial perspective, we order, receive, then value. And then we consign the valued inventory to the next step where we order, receive, value, and then consign that material to the next step of the process and so on. So the semiconductor process is really process manufacturing with discrete outcomes. There are a few other industries like it. None of them are particularly, comparisons that we like to talk about in the technology industry. So it's really, it's a bit unique in terms of this process flow and actually the inverted BOM process flow, the range of possibilities, a one-to-many production model. There's a few things that process and discrete outcome plan into it, and one of them is the assumption that the output of the previous step is the main input to the next step. And so we have something where that consigned material is something where we take it and we add value to it as it goes. We put a wafer in, we put it into inventory. And it may not stay there very long in your model, and then it may go straight to test, but the test process, maybe you don't think of it as adding value, but a probe process really goes through and says where are the good die and the bad die. And so in that particular way, it's added value to at least your knowledge of what's good about that wafer, the die that are actually useful. And so you can take the cost of the wafer and the cost of the test step and allocate that to the good die in the wafer. And then, the next step is an assembly process. And so that's going to be something where we take it through a die saw and we take it through die attach, and we do all these processes for assembly. But really, the output of the preceding step is often the main input, and usually the main input to the next step. And we really are focused on this core material plus value add at each stage of the process. We do define those major production stages, inventory points we talked about. If you're doing external manufacturing, if you're using a supply chain or fabless model or fabless steps, a lot of times we would call them at Tensoft pay points. And so a pay point is defined as, when you negotiate with your vendor, where are the points that they can invoice you at? Where are the points where they say production is done here, I'm going to invoice you? And for us, those pay points become valuation points. It's a point where there's a receipt accrual, there's a transaction valuation, and there's an invoice that will be received at a future point. If you have internal production steps, the production stopping points are also the valuation points. And so if you pull something out and run it through 3 workstations and then want to put it back into inventory, it's really the accumulation of the steps that occur concurrently, and sometimes it relates to the material value add or how you want to do the costing as well. But you come up with the production stopping points for internal valuation as well. You will have a little more control over the variables, such as where the material value add steps, where's the significant value change, where are the inventory value points that occur. And all these stages are really adding value to the original material. Now, I know we just said at the beginning that the output of the preceding step is the input to the next step, but we also have this complexity where the output in total is not often the next step input. And so the difference between those two is that a wafer would go to sort, and so the sort process would have wafers coming in. But if you think about this last one here, because especially if we're doing an outsourcing model or even internally, each one of those steps, the fab, sort, assembly, test process, may have a distinct or a different lot size. And so what comes into out of sorted die isn't necessarily the size of the lots. And so maybe you have 5,000 die in a wafer, but the assembly lot size is 10,000. And so, I mean, it's just, or it's 8,000, so it doesn't even fit neatly into one. And so the lot sizing between the steps is different. The yield impact between the steps has some impact of all the material moving or not. And so we do have this assumption that the output of the preceding step is part of the cost of the next step. But in reality of how lots move, inventory can be held at all those different points. Even for a planning model, if you have a push-pull model where you're building the die bank based on forecast and building to order the finished goods based on confirmed backlog or bookings, and so we have this different types of complexities here. So you end up with something here that kind of takes that information together, our same chart where we have the order, receive, value, consign, order, receive, value, consign process, and we look at these built-in inventory points or valuation points between the steps. At the beginning, we don't really have the material, consigned material in, unless you're buying epi wafers or something else there. So we have this value add, we have the calculated yield, probably 100% for fab, and then we have this output valued. The next step that we do here in the process, we have the input added, and so now we've basically taken those same 3 steps, but we add in the value of the consigned material. And so we have input material, value added, yield calculated, output value. And that process, in terms of our repeatable production steps, our repeatable production control, is also the repeatable process that can help us with inventory evaluation and inventory costing. When we think about the cost here for the standard cost or in the semiconductor world, we have our cost for the step. We have the yield for the step, because sometimes we put in 1,000 and we get out 900, and really thinking about yield, and usually that means test yield. That could mean other types of yield impacts as we go. So we have these step costs, we have the step yield, and then we have the input from the preceding step, or the output from the preceding step, the input material, are really our cost sources as we go through this process. So for our planned step costs, we can have outside supplier cost, our vendor cost, and that's probably one of the more predictable ones in an outsourced model, where we can say with our suppliers, we negotiate what the price of a package is going to be for the next quarter or the next 6 months. We have internal allocated costs, which in a pure fabless model you may or may not do. We'll talk a little bit more about when those come in and the types of things you can do there. And then we have these consumed material costs, which are really sort of material beyond the input that would be, say, a substrate that you might cost at the assembly step, any other types of materials you might consume for an internal process, and really sort of fixed. These are usually higher value materials that you would issue out of inventory and track and move into production. We have our planned yield. And really, most commonly, the planned yield is something where if you're looking ahead, and this is really operations and finance together, putting their heads together to say what's our planned yield. I think for a quarterly model, it's fairly common to look at what's the yield plan in the month 2 or at the end of month 2 within this quarter, and then you kind of measure yourself plus and minus that, where if you have improving yields, your yields may be higher than that planned yield for the first month and a half or 2 months, and after that you're going to get positive yield variances and so on, and you can monitor the direction of yield as part of the cost. And then this production output flow. And so it looks, something along, well, I think I actually have another model for that. I have the internal cost or allocated cost here. So this is sort of those 3 cost scenarios there, or the planned step cost. This is really how people do the other types of costs, and these can be an internal production step. So if you have an internal test floor, you'll need to capture that cost somehow and move that cost into the inventory. And so it works for that. There are times where even if you've outsourced test, for example, maybe your company owns the test equipment, and so you want to take the depreciation and maintenance for that equipment or any other costs that you're paying directly and allocate that cost to the inventory. There can be other scenarios too where we've seen people do anything from freight to royalties to other types of costs that you're looking to put into inventory. I'm not recommending overuse of this model. It does add some steps to your production process, so there needs to be a legitimate reason to defer cost in terms of capitalizing in the inventory. But if there are significant timing differences between inventory creation and inventory cost recognition, if their inventory turns are a challenge, or at different velocity than you like, or whatever reason, there may be some reasons to use these cost scenarios, and certainly an internal production step would force those. We have the cost allocation is really an absorption accounting model where we set up a financial cost center in our ledger. We track the absorption of material into the inventory that ran through the process in that period, or quarter or month. And then we manage our over/under absorbed inventory value or cost center allocation. And this becomes another type of variance where you have an internal cost, you have this variance here for the over/under absorbed that you need a model to support and take care of. So in our particular example here of the internal cost, we've got labor costs, test equipment, test maintenance, facilities allocation for our internal test center, the subtotal cost, and then we're actually absorbing that into inventory at a cost per unit. So we have 48,000 units at 28 cents, and so we absorb 13,440. So we have an under-absorbed cost amount of 5,200. And it's really, if you think about this model, and pulling cost into inventory, what we're looking to do here is to isolate the cost that would be in this internal cost or general cost allocation pool. We are estimating the throughput and the value of that throughput and how that throughput would be allocated to different material. And so a lot of times test time might be the thing, and so you might have 2 or 3 different products going through your test floor, each one of them having a different cost per unit, basically because each one of them has a different required test time on the equipment or a different type of parameters, you know, that drive the cost per unit. So if we step back and look at our semiconductor costing in general here and just walk through a simple model where we have step cost, step yield, and we consider the input value. Here's our fab process where we go out and we say we're buying a very expensive wafer, $2,000. I know nobody buys $2,000 wafers anymore, or unless it's sort of exotic materials, but expensive wafer, $2,000, 100% yield, and we get this $2,000 out. Now our next step is our probe process, and I know we cost that, or we pay the supplier by wafer, and so that's supported in the procurement process. For costing purposes, a lot of times when it comes out of sort or probe, we know the number of good die, and so we really want to cost a good die. So in my assumption here, I'm going through and saying the cost for good die or per die is 25 cents. And I have an input value from the preceding step. So this input value is really the assumption that the output of the preceding step becomes the input to the next step. And so I have a 200-to-1 wafer to die conversion. So I've got a $10 equivalent die on my wafer. The equivalent cost for this step is 25 cents for the test. And so I've got a cumulative cost of $10.25. What I need to consider then now is the impact of yield. And my planned yield at this point is 90%. And so the equation is really to take that $10.25 and divide it by the planned yield, which yields the cost in the semiconductor terminology to say that the cost per good die is $11.38. And if you think about the equation here from a costing perspective, if you had 1,000 die at $10.25, or if you had 900 die at $11.38.89 cents, that's going to be the equivalent dollar value in the end. And so really what we're doing in this industry is we're saying, you know, scrap is not, we don't throw away scrap material. We don't throw away 10% of our inventory at $10.25 into a scrap pool. What we do is plan for the yield, and we plan for the yield in a way that says the planned yield loss becomes part of the cost of goods. It becomes part of the value. That has a couple of impacts. One of them is that our product cost becomes a more accurate reflection of the input costs that actually took to get there. So it's a better assumption for when we're looking at our cost of goods in the end. But the other one is that if we think about standards again as a plan, we're going to plant a flag and we're going to manage to this, yield becomes a huge impact on cost driving. And so when we're thinking about how do we partner between operations and finance to reduce the cost of inventory over time, it really becomes one of the key drivers can be how do we improve our yield. You know, a small percentage improvement in yield can have a big impact on the cost of the output. So what is it that can be done to drive that? My example continues here through assembly where I have 11.3389. I'm adding a couple types of step costs. I've got a supplier who's charging me $6 for the assembly process. I'm providing the substrate at $2, and so $19.3389 for the subtotal, and then I've got a planned yield of 98% because they break some die, getting them ready, and then putting them in the forms and so on to go through the line. And so my planned cost there again is yielded at 19.7846. So really, if you think about standard cost and the meaning of standard cost that we're going to plan and set our variables, and then you think about semiconductor being a process manufacturing with a discrete outcome, this range of possibilities, this inverted bomb process flow. This here really is where the costing comes together. This is the core basic model of semiconductor costing, where we take the input plus the step cost, we yield it, and that gives us our planned output cost.